Welcome everyone to Forecasting Can Get Easier Over Long Timeframes. Our speaker today is Toby Ord, a philosopher at Oxford University, who you may have heard of if you've poked around this effective altruism thing a little bit. Toby co-founded Give 'Em What We Can back in 2009, and in the years that followed helped to launch the broader EA movement. And his 2020 book, The Precipice, is a landmark exploration of science and ethics of existential risk, which I can highly recommend if you haven't read it already. His work nowadays focuses on big picture questions facing humanity, like what are the most important issues of our time and what can we do about them, which feel like pretty sensible things to think about. So I'm going to turn it over to Toby in a sec to talk about forecasting things over longer time frames. But first, just want to remind you, your big perk being here, as opposed to watching in the future on YouTube, is being able to participate in the Q&A. So would encourage you to open up Swapcard right now, click on this session, the little live interaction button, and then you can put your own questions there as you think of them during the talk, and also upvote others' questions so I know which ones to ask first. There'll be another chance to ask questions at office hours right after this in Aurora 16. Arthur there will walk us over afterwards, but that's just right upstairs next to the room where we're all having lunch. And so would encourage you to also save good questions for that moment as well. Okay, please join me in welcoming Toby.
Hi. Okay, so we're going to be talking about forecasting here. And I hope that at least some of you find the idea that forecasting can get easier over long time spans counterintuitive. So I no longer find this at all counterintuitive, and now I've started to worry that maybe no one else will as well. So here's what I think of as the kind of standard view. That it gets systematically harder to forecast over these longer time horizons. So for example, if it's currently the year 2000, which I will keep assuming in this talk in order to make my numbers clean, and you're making a one-year forecast about 2001, that it would be substantially harder to forecast the same question about 2010 or 2100 or 3000. So yeah, I want to show of hands of how many people have that intuition. Or at least maybe some of you are losing it a little bit because the whole purpose of this talk is to suggest that it's not true. Okay, good to hear. Even if you think, no, it doesn't get harder, hopefully you'll enjoy seeing why not as I try to kind of expose the particular reasons. And we'll see where we end up on this. I think it's possible that like me, you'll end up just previously thinking you were not confused about this question, that obviously it gets harder, and then at the end, maybe ending up a little bit confused. I feel now that I'm like, I wonder about why people ever even thought this, and so on. So I'm in a position that's somewhat confused. I think in the questions we'll try to dig into that a little bit. Okay, so here's what I think might be going on in this standard view. With this idea of compounding uncertainty. So we have a reasonable understanding of the current state of the world and the direction it's headed and the dynamics through which it unfolds. But this understanding is limited. So over time, any errors in this understanding compound. And we start with a moderate amount of uncertainty, but over time, the range of this uncertainty expands. So if you imagine you're looking at like a single frame of a film, and you're trying to work out, what happens next. Maybe you've just kind of gone outside on a street scene or something like that, and there's a whole lot of people kind of in the middle of moving. If you're trying to predict the next second, you're pretty clear their bodies will be in roughly the same places, where their arms will have started to move and so on. But then if you're predicting, over 10 seconds, 20 seconds, as the time gets longer, there's kind of more divergence in the kind of paths that everything can take. Maybe it's something like that. And this divergence seems to be increasing with the nonlinear types of effects. Okay. Now, my view is that there's no systematic relationship between whether forecasts get easier or harder over time, and that many forecasts get easier over longer time periods, and many also get harder. And I'm going to look at a few examples, but mainly what we're going to be doing is searching for the mechanisms behind this. So why is it that some forecasts get easier to make over longer time periods? And I think that it's not just one answer, there's several answers, and each of them is quite interesting. And then I think that this is relevant for both people who set long-term forecasts, so who ask how to ask the right questions. And I think that at the moment, the forecasting community doesn't set many long-term forecasts, and I think that they should do more, because I think it's quite possible. But it's also relevant for the case of being a forecaster and doing these types of things. How would you think through this process of predicting these things? And the thing that's closest to my heart is about reasoning about the long-term future of humanity. So at the Future of Humanity Institute and at Oxford, and also as part of the long-termism community, I think it's really valuable to think about the long-term future of where things could be headed, and I think that this is possible, not with certainty. And if it is the case that for many questions, predicting them becomes easier over long time frames, that helps to support that kind of picture, that it's not futile to be thinking about the long-term future. As opposed to the view that it's hard enough to predict what's going to happen in 3 years, 300 years is just insane. It's obviously nonsense to try to predict anything. This it potentially pushes back on that. Okay, so here's the first mechanism that I want to look at, which is cumulative chances. So suppose for the sake of easy calculation, it's the 1st of January, the year 2000, because I do need to use dates for some subtle reasons. And so this way, the dates will all be clean as to what we're talking about. So consider this question: will a war kill more than 1 million people by 2010? Or will a war kill more than 1 million people by 2001? Or will it kill more than 1 million people by the 1st of February? Or alternatively, will it kill more than 1 million people by the year 2100? So if with this first 3 questions, as the time frame is shrinking, it is becoming easier to answer these questions, right? And the answer is increasingly strongly, no, it won't. Because it's quite unlikely. Ultimately, there were several wars that killed more than 1 million people in the 20th century as a base rate. So the chance that one happens in the next month is going to be generally quite low. And the chance that one happens in the next 10 years, the first of these questions, is actually pretty hard, because that's actually at around about the most difficult, for something that happens, say, 8 times a century, will it happen in the next decade is a pretty difficult question. But once it's in the next year or in the next month, it's getting easier. But if you look at this question here, will it happen in the next 100 years? It starts to become a bit easier again. The answer is yes, probably. Like maybe 80% or 90% confidence or something like that. Certainly, if there were several in the year, I think it's 8 or so in the 20th century, it seems quite unlikely there'll be 0 in the 21st century. So once you have a cumulative type question, it can get easier to predict over long time frames. Will war kill more than 1 million people by the year 3000? Then it's like, oh, yeah. I mean, unless something really different happens, you'd expect that to be 99% probability or higher. So you could have very confident predictions on a question like that. So here's how I view this. That this type of question, where you're saying, will something happen by a certain year, is a cumulative chances question, where what's going on is like there's a kind of cumulative probability that keeps increasing as more years go by. It can never go down. If you've got a type of question like the one I've drawn here in orange, where the probability goes up towards 100% as time goes on, then it moves through this kind of hardest to predict zone somewhere in the middle, and then moves back into an easy to predict zone. So this helps to explain why it is that they do get easier to predict over very tiny time periods, but then they get hard to predict and then they get easier to predict again, is as it moves through this. Now, that doesn't have to happen. It could be that the curve gets stuck at about 50%. Maybe the very long-term probability of something, ends up in that zone. For example, you're trying to work out, will we have a certain technology by a certain time? But there's also a chance we never get that technology. And so therefore, it kind of could stall out at some level short of 100%. But for questions that aren't like that, I think you often get this effect. So we could think of in questions, like where you're saying, will something happen in this year? And by questions, will it happen by this year? And for the by questions, they do often become easier due to this cumulative chances. So this is You don't have to be able to read these. This is the first, I think, 20 questions from a famous paper that was the paper that led to the idea of super forecasters. So this was a forecasting tournament by Tetlock and others. That this is just the first 20 questions on their list. And what I've done is in bold, I've put the questions that are by questions. And so you can see, I went back to this data set because I thought it was, one could always ask, well, for some questions, maybe it gets easier over longer time periods, but and maybe if we let Toby just choose his own questions, he'll pick all the ones that are helpful for his own argument. So I thought it was nice to go back to this kind of famous canonical set and then try to have a look at what happens with the questions in it. So you can see that there are a lot of by questions, such as will Italy's Silvio Berlusconi resign, lose re-election or a confidence vote, or otherwise vacate office before the 1st of October 2011. And you can see that as you just increase 2011 to to 2021 or 2050 or the year 3000 or something like that, the probability of this thing is just going to keep going up and it's going to go into the easy zone. And so I'm going to shade here like a set of these questions where I think they do get into the easy zone. But in some cases they don't, like, will Serbia be officially granted EU candidacy by a certain date? It's not clear that if they would ever be granted the EU candidacy, so that one maybe doesn't get out of the hard zone, but a bunch of them do. And we'll come back to this as we look at more mechanisms. Okay, so here's the second one, which is I call windows of relevance. So consider a question about a very successful politician in the US, Sydney, who may one day try for the US presidency. Maybe Sydney is currently a senator. And there's this question, will Sydney be the US president in the year 2010? So asking about 10 years' time. And that could be an interesting kind of political forecast question. But if you ask, will Sydney be the US president in the year 2100, unless something very weird happens in the world, the answer is just going to be no, so a high probability for no, so very low probability for this thing. So the way I think of this is an in prediction, not a by forecast. But it still gets harder to predict in some intermediate time zone, right? Which is this kind of window of relevance. There's a time when this probability creeps up, but then the probability is going to go back down again because it's just not plausible that this thing is going to be a relevant contender in the long run. So there's a bunch like this as well, which get easier and then get harder and then get easier to predict again. And so here are some more. So will the six-party talks formally resume in the year 4036 or something? That's a pretty easy question. No, the six-party talks will not resume in that year, whatever they are. And so there are a bunch of these types of questions that just get easier to predict as you take these dates and just make them higher. And so now we've actually got quite a bunch of these questions, the types of questions where if you ask them on longer time frames, they just get easier. Okay, here's a couple more of these mechanisms, which I call attractors and absorbers. So imagine a rock on the slope of a bowl-shaped depression. Maybe you're out hiking in the countryside, and you see a rock, that's somewhere up the slope on this the Over time, if you had to predict where it will be, you'd expect to find it closer to the bottom of this depression. There's the force of gravity acting in this system. It's not enough to just make this rock roll all the way in, but if there are kind of gradual it gets pushed by a sheep one day or something like that, it's unlikely to roll up the hill, whereas it's more likely if it gets pushed to roll down. And you would expect this object to be slowly, there's some kind of force pulling it in towards this central place. Okay, so that's the rock being at the bottom of this depression would be the attractor state. And so attractor states help with long-term prediction of continuous quantities. And so these include a bunch of different things. This isn't a complete list, but things like stable economic or game theoretic equilibria, where you might expect that over time things approach the equilibrium dynamics, as well as states where an agent has fulfilled its goals or preferences. So if you have an agent who's getting hungry and is kind of looking for food, you might expect that eventually they surmount the obstacles to them finding their food and actually succeed in meeting that preference. But also broken down states. If you ask, what condition is a particular car going to be in over time, when there are systems that could get damaged in various ways that will degrade their performance, it's a bit like entropy increasing in a system, that you'd expect this kind of general kind of force or attractor state towards a broken down condition of something. Absorbing states are related, but are slightly different. So imagine a golf ball on a flat golf green with no humans nearby no one's putting this ball, and we're trying to predict where it's going to be in the future. Well, the golf hole doesn't attract the ball in this case. It's not that it's going to roll towards it of its own accord. But if this ball has just been kind of knocked around randomly by the weather or animals or something like that over time, if it does enter the hole, it's not going to be leaving the hole. And so it can be an absorbing state without being an attracting state. They're separate concepts. Okay, and so there are a whole lot of examples of this, such as if you break a system, that can often, it then can't continue. So death of humans or other organisms, extinction for a species, a company being wound up, or a quantity necessary for survival dropping to zero forever and staying at zero. So they could also be, as an example there, world GDP. If it goes to zero, it's presumably at zero forever. So this is true for a lot of quantities. And it could also include positive irreversibilities. It doesn't have to be negative. So if there's been some problem, such as how to deal with superannuation, and finally solve this problem that the government's been facing, you might expect that eventually they do work out a solution to the problem and then it stays fixed. Maybe that's one that becomes broken again. So it could depend on the exact problem. But fixing problems, can be an absorbing state as well. Okay. Although on the list of things from the forecasting tournament, there weren't any that those mechanisms help with. But I think that they're helpful for thinking about a lot of different long-term forecasts. So here's another one, the law of large numbers. So longer-term prediction can become easier due to random fluctuations eventually cancelling each other out. So if we have some random variable x, and it's the sum of n different independent random variables, and their variance of those random variables is similar, then there's this famous result that the standard deviation of x, so a kind of measure for how big a spread there is of dispersion of this quantity, it grows as the square root of n. Okay, so that's the mathematical result that's going to be doing this work, and I'll give some examples. So what happens is that the uncertainty grows as we have more and more of these random variables that contribute to this thing. But it doesn't stack linearly, and that's what does the work here. So as an example, if you flip 1,000,000 coins, most of the heads that you flip will cancel out with the tails if you're trying to work out the average, or if you're trying to work out the net amount of heads. And it will leave typically only about 1,000 heads or tails uncancelled, because 1,000 is the square root of 1,000,000. And so the absolute prediction error, if you're trying to work out how many heads will there be, or how many tails, or what's the net excess of heads over tails in this case, as you add more and more coins, you're going to be out by larger and larger numbers. If there's only one coin, right, the most you could be out by is a half, if you say there'll be half a heads. Whereas as you add more and more, the absolute prediction error grows. Okay? But the relative prediction error decreases. So as in percentage terms, you're going to have less and less error. So there's a few different ways to look at this. So one is that for any of these areas where you have a lot of independent random effects over time, all adding up, the prediction error of the total will increase in absolute terms. That's the sense in which it's getting harder to predict over time. But if you're trying to predict it, you're trying to think about it in percentage terms, then the prediction error decreases. And I think that part of the question here is, if you're trying to predict a quantity over a long period of time, such as the GDP of a country or something like this, or how large a sector is as part of the economy or things, there's a kind of question of like, are you generally interested in the absolute values or the relative values? Like, is it reasonable to score it based on one or the other? And I think that the answer for a lot of things is actually the relative values. So if someone said, oh, it's really hard to predict GDP as time goes on, because in the year 2100, we could be off by, GDP will be so high, instead of like world GDP, say, being 100 trillion like it is now, it'll be some much higher amount. And you could just be wrong by more than $100 trillion in your estimate. I feel like that's not that relevant. If you got it to within 1% of correct, that would sound like a very accurate prediction. And the fact that you might be off by 200 trillion when you're doing it is neither here nor there. So I think that the relative prediction error is often the correct kind of measure here, in which case it can decrease, it can become easier to predict over time. So suppose, for example, that there will be a bunch of recessions and periods of growth, each of which is hard to predict, but you might be able to predict roughly the number of recessions over some period of time, even if every one of them is hard to predict, like a coin toss. And I also put here that the prediction error of an average, if you're trying to predict the average, then that decreases even in absolute terms. So, for example, if you're trying to predict the average rainfall over some period of time, that becomes easier in absolute terms as the interval gets longer. So if we want to know how much rain was there per day, and we're trying to predict how much rain will there be per day over the next week, or the next month or next year, if we go to the next 50 years or something, it's starting to become a lot easier. We can just predict the general average from the historical record, possibly adjusted for climate change or something. But generally, it's becoming easier because these fluctuations are cancelling out. And predicting the total rainfall over an interval would become easier in percentage terms, but not in absolute terms. Okay, and so here's a related idea that can illustrate this. So a random walk is this process where you can imagine you flip a coin, and if it's heads, you go up by 1 unit. If it's tails, you go down by 1 unit. Or maybe the coin is biased, or you use some other process. Something like that is called a random walk. And what happens is that you can see these trajectories over time kind of sketched out. They look a lot like stock market traces. And the theory of random walks has been developed in concert with financial economics and understanding of stock markets. And what happens, though, over time is that prediction error becomes small relative to the full possible range of things. So you can see that this likely range is growing as the square root. It's got that kind of curvature to it, whereas the full possible range is growing linearly. And if a random walk is biased, so suppose that there's a 60% chance it goes up by 1 and a 40% chance it goes down by 1, then what you get is the likely range is kind of drifting up here. And if you were asked a question such as, will this random walk be above its starting value at time t, then the longer that time is, the easier it is to answer that question with, it just gets more and more confident that the answer is yes. And so that one is applicable to the stock market. So if you're trying to say, will the stock market, be higher than its current value in a month's time, it's very difficult. It's about 50% chance. Whereas if you're asking, will it be higher than its current value in 10 years' time, it's become quite easy. And in 100 years' time, easier again. It's the prediction error for the relative values, for regular random walks would also become easier. But as I kind of say here, that's not quite true for the stock market and GDP, to do with the fact that they're actually random walks in log space, like a logarithmic space. So unfortunately, I can't claim that one for the actual stock market. Okay, so this law of large numbers and the fact that they can have a lot of little effects cancelling out. This one I also get to shade in I don't know what color that is, a couple of additional questions here, such as will the Nikkei 2020 225 index finished trading above 9,500 on the 30th of September 2011. Is an example of one that becomes easier for these reasons. Okay, so that's the mechanisms that I want to look at. So we got to the point of shading in something like 2/3 of these questions as becoming easier over time. Maybe some of the others do as well, or maybe one could dispute some of these exact examples. But I hope this shows that, at least for the types of questions that are often asked, really a lot of them, if you ask them over longer dates, do actually become easier. Okay, so here is a puzzle with this, which maybe has occurred to some of you already, as part of this process of becoming more confused about this topic that might be happening. If so, hopefully this will make you a little bit less confused. So consider an event that happens in the year 2050. Isn't it always easier to predict that event the closer you are to that time, right? So if you're trying to predict it in 2010, that's easier than predicting it in the year 2000. If you're trying to predict it in the year 2040, it's going to, you're so much closer into it that more information about it's going to have been revealed to you. Or if you're predicting it in 2049, now even more information is available. So isn't it the case that actually the shorter the time horizon just makes it easier to predict? And then isn't that true for every possible event? I think actually it is true for every possible event, but it doesn't contradict the topic of my talk. And so that's a bit confusing. So here's how I would draw this scenario, right? There's an event, E 2025, which is we're trying to predict. And we're making predictions at a whole lot of earlier times. And each of those predictions is about this particular event. So in that scenario, I think it is actually getting easier the later your forecast happens. Whereas the topic of this talk has been about this second picture, where there's a current time now, and we're trying to make predictions about a whole lot of other times. And I'm suggesting that it need not get harder to make predictions about later times, and sometimes gets easier. And they're similar pictures, but they're not quite the same picture. And so, in the first example, it's a forecast at a particular time, T1, or I guess in both of them, forecast at T1 about time T2. And if you lower T1, that's like the first picture. That makes it harder to predict. But if instead of lowering T1, you raise T2, the time that it's about, that may or may not make it harder. And if you increase the gap generally, and you don't say whether you're raising or lowering with them, you're just saying the gap's getting larger, then it's unclear which of these pictures you're talking about. And it's the unclarity about which picture you're talking about that's kind of creating some of this confusion, or the feeling that there's a bit of a paradox here. I think that's pretty much a resolution to that concern, but I agree that it can still leave you feeling a little bit confused about it. I guess the key thing is that if the current year is 2025, and we're interested in making predictions about, say, 2027, and then someone says, well, should we also be doing predictions about longer-term future? It's the second picture that's going on, where we're all at the same year, and we're trying to work out whether it's reasonable for the forecasting platform or forecasting group to be making these longer-term predictions. That is the second picture. So the fact the first picture is behaving differently need not worry us too much. Yeah. To summarize that, for a fixed event time, it's harder to predict it further in advance. But for a fixed prediction time, it need not get harder to predict events further in the future. Okay, so where does one end up with all of this? I do feel that some of you are probably feeling a little bit like, there's something still a bit weird about this. Are these the right questions? Is this the right way to interpret getting harder over time to predict things? And we can come to some of that in the questions. But here are the kind of conclusions that I think you can make from this. So I want to try to reconcile our intuitive picture from the start about things getting harder to predict over longer time periods with the types of arguments that I presented, showing that if you actually try to make it a formal, clear statement, that needn't happen. So uncertainty about the full state of the world continues to expand over time. I think that's generally true. if you're understanding the location of every atom or something as they kind of cascade through time. But for certain key aspects of the world, such as a value of a parameter like GDP or the population of the world or something like that, our uncertainty can sometimes narrow, even as it's growing in some other dimensions. So there's all kinds of questions about what will be happening in the year 3000, including like what clothes will everyone be wearing, what music will be available, things like that. There's uncertainty just exploding in a whole lot of different dimensions. But if you pick a particular dimension, the uncertainty in that dimension doesn't always explode. So as an example, if you've got like a game of pinball, it's like a famously chaotic system. It's designed to be a chaotic system, where it's very hard after a few seconds to predict where the ball's going to be in this setup. But if you're fundamentally trying to predict the question of where will the ball be, in a long enough period of time, the answer is it will drain down to the bottom and the game will be over. So you get this kind of nonlinear explosive kind of chaos of this prediction becoming harder to do. But then eventually that actually resolves itself for that particular question and can become simpler. So the entire prediction problem is becoming harder with time, predicting the entire state of the world, but different parts of it can get easier. And one of the things that most influenced me to write this was a talk that I was at. I wasn't thinking quite in these terms back then, but about 15 years ago by David Christian, who's one of the pioneers of big history. So trying to think of finding unifying principles for thinking about history on very long timescales. And he has a lot of disagreement with the scholarly historians, the kind of history community in academia, who tend to think that there isn't a subject of big history and that history is very unpredictable and doesn't have these unifying trends. And his answer was that they're correct because they typically study history at the biographical timescale. So thinking about an individual's life or Victorian England, so i.e. the life of Queen Victoria and the things that were happening over that kind of a bit less than a century type time period. And his answer was that, yeah, it is very unpredictable over those time periods. But powerful trends reveal themselves as you actually look at longer and longer time scales. And so perhaps a scientist could easily have not made the discovery that they made, but someone else would have made it. Perhaps a fragile piece may not have broken or broken in that time and in that way, perhaps like the start of World War I, but it eventually would have broken in some way. And he had this analogy to quantum mechanics, where if you're looking at a particular particle, you might not be able to work out whether it's a particular radioisotope. Working out whether it will decay in its half-life, is very difficult. But if you have 100,000 of these particles, then you can roughly say how many of them will decay. And that becomes quite an easy prediction problem, and you'll get it to very high accuracy. So he was thinking then in terms of that difference between having small unpredictable parts and these larger ensembles of parts. Although, interestingly, from that example, you could also think about my cumulative chances model, where it's very hard to predict at roughly the half-life timescale for a radioactive particle whether it will decay, but it's easier to predict once you take that time approaching infinity. Okay, so historians, he argued, tend to focus on the time frame of highest contingency, possibly because it is the time frame of highest contingency. That might, in fact, be why they are studying things on the biographical timescale, is they're drawn to these kinds of questions that have that contingency. And perhaps forecasting has done this too. So if we look at the types of questions that are asked, they're often asked, someone is asking them, and the person asking them wants to find out information. And you find out a maximal amount of information if you're asking questions where you're at about 50-50 as to whether the thing will happen or not. We tend not to ask questions where it's just completely obvious that the thing will have happened by that point in time, as they'd be giving very little information back to the person who's asking them. So maybe part of what's going on is that in a lot of these questions, they're already selecting this kind of time frame of maximum uncertainty or something. And that, indeed, if you ask over longer time frames, it may well get easier. And then another kind of thought I want to draw out is about skills for long-term forecasting. So it may be quite a different game to the short-term forecasting. So rather than simulating the present state forward in time, which is what works really well for very short-term forecasts, right, to really understand the current state of play and something about the dynamics or the direction of movement, and then to just project it forward a little bit from there. But I think that long-term forecasting is quite different. It's more that you have to think about the long-run forces, and particularly about limits or equilibria that things might be drawn towards. So trying to find these attracting states that it's moving towards, or trying to find absorbing states where once it enters them, it can't leave again. And then trying to understand, which such states exist and for this system, even if you can't quite see how it will get to them, once you know that it can't leave them, they then start to become salient. And so that might involve quite different skills to do with understanding the limits of certain systems. And it might require a different information set. So it could involve more focus on long-run trends in the data, and also long-run historical trends. And also, this kind of information, perhaps based on physical principles, about the long-term future limits, as opposed to detailed understanding of the current state of play. So we looked at these different things. There were the cumulative chances, the windows of relevance, the attractor states, absorbing states, and the law of large numbers. I think that was 5 different mechanisms that can make it easier over time. And I think there's probably more. I kept coming up with them while writing the talk, and it didn't really feel like I was necessarily running out of them. So there could be others too. And then finally, it's kind of the upshots of all of this. I think that there should be more hope than people generally had for extending forecasting to much longer time periods. And also that if people are trying to do that and make long-term forecasts, they should consider this list of mechanisms that I've drawn out there. And also that I think there's more hope for reasoning about the very long-term future. So these kinds of ideas about thinking about the long-term future of humanity, where might we be going, is often thought of as, just obviously impossible, since we can't even predict kind of smaller periods of time. But once you realize that actually in some ways it could be easier to predict the long-term future, like an example I came up with earlier today was, what's the growth rate in the year 3000 or something? Well, maybe that actually it's not that hard, and the answer should be about 0, because we don't know when economic growth will stall out, right? But there's strong reasons to think that it will eventually stall out, and that it will do so within the next few thousand years, because if you have cumulative, couple of % growth for thousands of years, you get to truly insane levels. So maybe it's actually not that hard to predict the growth rate. It could be very hard to predict the level it's going to stall out at, but it might not actually be hard to predict the growth rate. So there are a lot of these things. You just kind of see them through a different lens or direction, and then you can kind of notice that, oh, hang on, maybe that is easy to predict. And so, more hope for doing that kind of work that we were doing at FHI. And also that, I hope that academics who are studying the long-term future, that they extend and critique and explore these different kinds of mechanisms. Thank you.
Unsurprisingly, given that we are a fan of rigor in the EA community, we have several questions that are hoping to just pin down a bit more precisely what we're even talking about when we say easier to forecast. Does this mean like easier to put an almost certain probability, like 99% or 0.1% on it, or is it just easier to be calibrated on the forecast? Yeah, what do you?
Yeah, so I guess I'm saying that something like that your Brier score would be better on these questions. So the more accuracy on them. So you get, in scoring systems for predictions, you get more points if you predict a confident level, like so closer to 0 or 1, and then are correct. It didn't go the other direction. And so you'll be able to do that more with these types of questions.
Nice.
I think that's my answer.
Okay, that's a good operationalization. So I guess I'm wondering, you framed it at the end there that this gives us hope for reasoning about the long-term future, which is a great optimistic parse of this. But does it also mean it's like less hopeful to be an action-relevant task to reason about the long-term future, if the whole thing that we're saying here is probably at the right time scale, we can take for granted that a certain thing will or won't happen. This is sort of like pour cold water on the notion that it's like a useful thing to spend time doing.
Yeah, so something interesting there, particularly with so in order to come up with the examples for the talk, I tried to pick examples where it really was clear that the probability would go to 0 or to 100%. And so in doing so, there were ones that everyone could, I had to kind of pick ones that everyone could see would go to 0 or 1 in order to make the point. But that means that they're the kind of trivialist ones I could find or something, whereas I don't think they all need to be that trivial. So for example, there could be a bunch of these, if you're thinking about the long-term future of humanity, where somewhat subtle questions about physics end up determining these things. That people wouldn't initially notice it. I mean, maybe you're predicting something about GDP on Earth in the year 5 billion, and it's helpful to know that the sun will have expanded out to the orbit of Venus, and all of Earth's atmosphere will have been destroyed, and so on at that point. And then if you keep keep projecting forward to understand what's going to happen, or to understand aspects of entropy or chaotic systems and so on. For example, understanding the equilibria. You might actually need quite a keen understanding of economics or of game theory to be able to spot the equilibria in some kind of dynamic, and then to notice that over time things are likely to be drawn towards it. But I mean, maybe I should have included an example like that where it was initially not obvious, and then you add this extra ingredient of kind of domain knowledge, and then it becomes clear.
Are there questions that feel topical to long-termism or effective altruism right now that you think could benefit from this observation, where maybe we're missing some key insight that this framework would help us find?
So yeah, I'm not sure because I don't know exactly what those questions are. I guess I want people, we need people to be kind of have some place for people to be pooling these questions. So I've been interested in all kinds of questions about the long-term future for a long time, and there are certain styles of answer that I think I feel kind of compelled by. I mean, I guess an example would include, say, will we ever be able to reach other stars? And I think the answer there is, yeah, really, it's very likely. Partly because the things that are often pointed out about the energy requirements that are needed, that there are reasons to believe these energy requirements get pretty small over time. So, for example, it could be a lot of energy compared to 1 year of entire electricity production of the Earth, but that our energy production is probably going to continue to go up, and also over long time periods, you could just save up, 1% of the energy of the world and kind of put that into a cumulative kind of supply, like, leading up to being able to launch this spacecraft, or that technology is very difficult to predict exactly when or what the new technologies that will enable faster travel is. But it's actually not that hard to predict over time that some of these new technologies, the chance that we're at the zenith and nothing will ever go faster is actually really quite unlikely. So there are cases like this where I've kind of got somewhat settled views on them after having talked about it with people for a long time. And partly because there's often a bit of confusion when you talk about somewhat science fiction sounding possibilities. Even when scientists kind of make their claims that heavier than air flight is impossible or whatever it is and turn out to be wrong, they're often tacitly kind of saying in a reasonable time frame or something is like added onto their prediction, and that if they had have explicitly said that, they would have perhaps been correct. So I think I don't currently know what all the kinds of questions people are asking, but if I did, and which ones people were really thinking are open questions, I might be able to help close some of them using these techniques and point out that actually this one that you're really uncertain about is easier than you think.
Well, I mean, maybe one of the biggest one would just be, what can we expect, like the population of Earth-originating life to be in the long-term future? And it sort of seems like...
Well, really long-term future is 0. So that's an easy one for you using this technique. But so then you have to go back a little bit before that. Like, what's the peak it will reach before it goes down again? Or what's the cumulative population, the total amount that will ever live? Those ones start to become hard again.
So if people out there have done the math and said, I want to focus on working on AI risk, for example, because I believe that there's at least some chance of a hugely expansive Earth-originating future. are they making a mistake? Are you basically saying, look, the base rates tell you that long enough out, it's all going to go to zero at some point?
No, I mean, it's a somewhat glib answer, but it is a useful technique to know. Is just like if someone's saying what will some population be in the long term, you can kind of quickly think, oh, what if time approaches infinity? What's the limit? And often there is an easy answer. I think that this has often confused people and led to kind of some cosmic nihilism or something, when people kind of think that in the end, we'll all just be dust, and so will anything be worth it? Or on their own life scale, in the end, you'll just kind of, be in the grave and so on. So, what's anything matter? And I feel that's a massive non sequitur, that it's all about the journey. And there's all kinds of journeys you could take during your life, or during humanity's life, some of which are kind of very impressive and some of which would be deeply disturbing, and it really matters which ones we take. So I wouldn't want everyone to focus on the fact that in the long run it goes to zero as being all that relevant. The bigger question there is what happens in the medium term. I'm not sure exactly how many of these techniques you can apply, but I do think that the expected number of people, so one way of reducing a distribution down to just a single point, is extremely high. I mean, there are 100 billion stars, in our galaxy, and there are about 20 billion galaxies that would be reachable from here at the speed of light, and one could have many different lives of flourishing being lived around each of these things. And what's the chance that we settle our galaxy and then go on to settle other galaxies? I don't know exactly, but you'd have to claim that they're both like lower than 1 in a billion in order to get a small expectation here. And so that's a style of argument that shows that you would have to have kind of wild levels. Like, I'm 99.99999% sure that you're wrong. And then following that, I'm 99.999% sure the other thing's also wrong. And they're completely unreasonable levels. So the expected number is going to be high. But people rightly get some kind of qualms about just using expected numbers in these cases of really low probabilities. But I think actually that, let's say I think there's a more than 10% chance that if we survive for more than 1,000 years, that we ultimately either settle other galaxies or do something else with them. Maybe they're already settled by other alien species and we communicate with them and coordinate with them and so on. But that things are happening on these scales, and that I think is like quite a reasonable chance. Okay,
so maybe this is a good time to tease out the distinction between sort of forecasting the future as a fixed thing that will happen, and an exercise in like changing our uncertainty about that, versus forecasting what our sort of effect on the future might be if we choose to take or not take different actions. And the latter seems much more relevant to the project of trying to make the future go well. So when it comes to things like, yes, in the long run, we might have a population size that isn't expectation-related large, that's dominated by some worlds where we have a huge future, some worlds where we have one that's quite small or goes to zero. If I'm a person who wants to change the relative likelihood of those two things, do you think there's considerations here that are relevant to me? Like, does it give us information about how likely one intervention we do is to like bring us towards this attractor state or not?
Yeah, that's a great question, whoever asked that. So it's interesting, because at some level, if the changes you're making are not big, then I think that this type of reasoning suggests that if you're in some kind of dynamic, and that dynamic has some equilibrium, say, that things are going to be pulled towards, and you're not really changing things all that much, you're still just going to be pulled towards this same equilibrium. That was the power of the equilibrium argument, or the limit arguments, that it can't go beyond some level, so it will be driven up to it, and then it will have to just stall out at that level. Was that it doesn't really matter where it is now or how fast it's going. If that level stays the same, it's going to end up very close to that number. So the robustness of that type of argument, in order to be so robust, it has to be robust to certain kinds of small changes that one could make as a conditional forecast. But as the question, I think, slightly alluded to, if you can change the system, or maybe there's multiple equilibria, and it could settle down into this kind of absorbing or attracting kind of valley or something, or it could settle down into this one. But you're still somewhere near the top, and you kind of get some ability to steer which way it goes, or if it's possible to fundamentally change where the limit is or something like that. It suggests that those types of changes really could give big differences in conditional forecasts. But you would, and it helps to kind of draw one's attention to the types of actions that really change the game instead of just changing kind of where we are within the game.
Would you be able to offer a few concrete examples of actions that you see right now as being sort of hingy or good candidates for changing the game?
Yeah, so I think, I guess there's different levels at which you can do it, but I think it's pretty unclear how AI will play out in terms of, will there be, for example, a particular US project that's just a US national project, where the US tries to go it alone and not invite other nations in. That's one possibility. And another possibility is some kind of coalition of like-minded nations, perhaps including the US. I think that would be a substantially better world. But I could see that how things play out in the next couple of years could determine which of those pathways we end up on. So it could partly depend on whether nations outside the US kind of put up a credible enough kind of thing to show that they've got something to add to this, or that they've got kind of credible mechanisms for why it could be good. I mean, as an example, the EU GDP is, I think it's still higher than the US GDP, even if the GDP per capita is lower. So there's a lot of money. And so if a large part of what we need is compute, and compute just costs money, that is something that other nations could provide, even if they're a bit behind on some of the aspects. So, but that's kind of a case in the somewhat near term as to how those things shake out. Another example would be, I could imagine a version of humanity that gets its act together on existential risk, so that reaches this state that I call existential security, where we've got risk low and we've made commitments to keep it low. So as an example, we could even have a kind of commitment that the existential risk over the next century, from 2100 to 2200, has to fit within a budget of like 1 percentage point of existential risk. And then the next century, the budget is 0.5 percentage point, and it's kind of going down. So it may be impossible to ever completely eliminate risk, but if you make sure that these budgets go down quickly enough, then you can have a non-zero chance of kind of indefinite survival until some other kind of limit. And so you could imagine humanity that's on that course, where we've got something a bit like a constitution for humanity that binds our future actions. That it's like we can take all kinds of different paths if we'd like, but we have to kind of meet a certain constraint that we don't pose too much risk on future generations, and that kind of constraint binds a bit tighter each generation. So if we ended up on that kind of path, then the median survival time for humanity might be really quite long, versus if we don't.
Yeah. All right, we'll have to end on that
Okay.
hopeful note. We're running out of time here, but there are office hours right now if you want to follow Arthur and Toby.
Please come along.
And for now, please join me in thanking Toby one more time.